So let's suppose that you've installed some new software on your computer and hooked it up to a thermometer outside your house. And this software will measure the temperature outside your house in some location every minute over the course of a day. And at the end of the day, it has a reading that looks like this. So it's obviously a very weather-filled day. The temperature has changed a bunch of times over that 24-hour period. But you want to know, what was the average temperature for the whole day? And you can certainly add all of these, calculate whatever value the heights of these points represent at any given minute. You can add them all up and divide by how many there are and get the average. But there's another way to do that that's pretty simple. Let's remember back to algebra and algebra 2, where we talked about rates of change. And remember, rate of change just meant the change, this triangle meaning delta or change in. And we usually looked at change in y over change in x, just rise over run. That's the slope of a line. And so the slope of a line gave us the rate of change over the entire life of that line. Easy enough to do with a line because a line doesn't curve and go up and down like this does. It always has the same slope. But we can use the same idea to evaluate the average rate of change on some other curve. So imagine that this point represents the change in temperature after 1 hour of measurement, or let's say 60 minutes since our measurements are in minutes. So after 60 minutes, the temperature has obviously gone up a little bit, and it seems to have gone up almost linearly. It almost looks like it's a line. Let's see if I can trace it better. There we go. It almost looks like it's a line. So calculating this change in temperature would be super easy if I just use the equation we are used to using to find the slope of a line. So let's say the starting temperature that day was 20 and the ending temperature after 60 minutes had only gone up by 2 degrees to 22 degrees. So the rise over run, or the slope equation, m equals whatever the change in y is over the change in x, and the change in y is 22 take away 20, and the change in x is 60 take away 0. So that's 22 take away 20, and 6 over 60, which equals 1 over 30, which represents 1 degree per 30 seconds. Or 2 degrees per minute, if I want to write it using this form, depending on how I want to talk about it. The point being that the slope equation will tell me what the change in temperature from some starting point to some ending point is. And it's the average change in temperature. So don't be fooled by the fact that it's linear here, because if I go 1 more hour, so 120 minutes, now I'm looking at a temperature up here, and let's say that's about 30 degrees. So I can say that the change in temperature, I can see just by looking, and because I'm familiar with how temperature works over the course of a day, the average change in temperature in 2 hours is 10 degrees. So that would be 10 degrees in 2 hours, or 5 degrees in 1 hour. Easy enough to see, but let's look at it a little bit closer. For the time distance between 1 hour and 2 hours, you can see that sometimes the temperature was lower than 30 degrees, and sometimes the temperature was higher than 30 degrees. And so what we want to know is, what is the average temperature from when it was between the lower than and the higher than, until it finally settled in at 30 degrees at exactly 2 hours. And again, the secant line will give us that average. So I probably don't need to draw that second part. So if I can find a way to represent a starting point and a finishing point, then the secant line can give me the average rate of change from 1 hour to 2 hours in this day that I've recorded all of this data for. It doesn't say anything about when it was less than that average amount and when it was higher than that average amount. It doesn't say anything about that. It just says that if I'm going to look at the time period between 1 hour and 2 hours, I can find the average rate of change by looking at the secant line, the line that connects through those 2 points. So if I want to know for this second hour of the day, then again, I would just use the slope equation, change in y over the change in x, which in this case means y representing temperature, so the change in temp over the change in time. So the change in temperature for this hour, not the whole day. My verbal example earlier was for the whole day so far, the whole recording part of the day, but we just want to look at a portion of it. So I'm going to take this value where we went from 30 degrees or from 22 degrees to 30 degrees, and that change would be represented by subtracting 22 from 30 and then subtracting 120 from 60 will give me the change in time. And so 30 take away 22 is 8, and 120 take away 60 is 60. So I could say that this means that the temperature changed 8 degrees per hour, if I want to look at it that way. Or I could continue to reduce this and get, let's see, 4 and 20, so 2 and 2/10. Oh, I can go even farther than that and say 1/5. Oh, that's Porter Puppy still helping out with my math lessons. Had to pause for a minute while he had a little tantrum. So where was I? 8 degrees per hour or 1 degree every 5 minutes. Now that's a pretty fast temperature change, isn't it? Even though that's just the average over an hour, that's a pretty fast temperature change. But notice that the average really talks about a fast change in temperature all the way from here to the top, super fast change in temperature, and then a little relaxing, maybe a cloud or two came out, and so the temperature went down when the sun was blocked. If I wanted to know how fast, on average, the temperature changed in that time period, all I would have to do is figure out what was the time lapse, right? Well, how long did it take to reach that high point, and how high did that high point get? I'm not going to put any data in. I think we've already exhausted the value of this calculation for finding averages. And you can imagine by looking at the course of a day, if I wanted to know what was the average temperature over the course of a day, I could take a secant line that started from the first measurement, take it all the way over here, and it would include all of this high temperature over some length of time, these lower temperatures. Oh, it got higher, but not super high yet, and then back down and then back up. I could disregard all of these little changes and talk just about the average temperature over the course of the day if I could calculate the values from the secant line. So the secant line through any curve will give you the average rate of change for that curve over the life of that curve. So let's look at an example. Suppose I want to know the average rate of change on the equation that would be graphed y equals, let's say, x squared minus 3. Over an interval, let's see, from 1/2 to 5/2. Okay, so I'm not actually trying to find out. I don't even need to graph this graph. We know it looks something like this. We know that it goes down, it's a basic parabola, symmetrical about the y-axis, and the vertex is at -3. And so we know it looks something like this. And we want to know what is the average rate of change from 1/2 to 5/2, wherever that is on the parabola. So these are imaginary points I'm kind of making up. I don't really know where they live. I don't really care. I'm not even going to graph it to find out, because all I have to do is find out by plugging in my values. So I'm going to say the function of 1/2, or the f of 1/2, equals 1/2 squared minus 3, and that equals 1/4 minus, well, 3 is the same as, oh, no, I want to keep my 3. So if I multiply the 4 in the denominator, 4 in the numerator, I get 1 minus 12 over 4. So that's negative 11/4. I know, you're thinking that's a totally ugly number, but I'm thinking there's nothing wrong with that number. All I've done is found that I have a coordinate. My first point, the coordinate that I'm going to check, is 1/2 on the x-axis, negative 11/4 on the y-axis. And then let's find the value for the other point. The f of 5/2 equals 5/2 squared, just substituting, minus 3, but that's 25/4 minus 3. Multiply 4 into the numerator and the denominator, and that gives me 25 minus 12 over 4, which leads to 25 take away 12 is 13/4. So my guessed picture is pretty accurate. I have a positive value at the input value 5/2 for x, and I have a negative value at the input value 1/2 for x. And so my second point is 5/2 and 13/4. Okay, all I have to do now is use my average change, or my rate of change, or my slope equation. So I have to identify which point I want to look at first, and I think I'm going to make this my point 2 and this my point 1. So let me give you a bunch of information to tie it into your history. We know that the slope is rise over run, and another way of writing that is change in y over change in x, and the change in y would be the y-ordinate from point 2 minus the y-ordinate from point 1 over the x-ordinate from point 2 minus the x-ordinate from point 1. So y2, 13/4 minus y1. Well, you know what I might want to do before I do this? Let's rewrite our points so that I have 4 in the denominator everywhere, because it's going to make this job so much easier. So before I even write out the rest of my equation, I'm going to go ahead and convert this to 2/4 for my x value, negative 11/4 for my y value. And then this one, I'll convert, let's see, 2 times 2, so 10/4 and 13/4. Okay, so if I haven't made a calculation error in my head, then these two coordinates are exactly the same as these two coordinates, because I've just changed the look of my fractions without changing the value of my fractions. So now let's put it together. 13/4 y2 minus y1, which is 11/4. So a negative times a negative, or a minus minus, is going to make this a plus. Since I have the same denominator, I'm going to add numerators, so I can just write 11 in the numerator and carry it forward that way. Then, in the denominator, I'm going to do the same thing. I know that the denominator of the denominator fraction is 4, so all I have to do is whatever arithmetic on the numerators. And so I have 10 minus 2, and now let's simplify. 13 plus 11 is 25/4. Well, I'll keep it as division at this point, over 8/4. I'm going to keep it fourths. 8/4. I know I can reduce this, but I'm not going to, and you'll see why in a minute. So now just convert this to multiplication. 25/4 times, flip the denominator, 4/8. That's why I didn't change my denominator. It's just as easy to cancel it that way. And so I get 25/8 is the average change of this function, right? So the rise of this function divided by the run of that function, the average change between these 2 points. Notice that the parabola isn't a line, so the parabola itself doesn't change in that slope, but at those 2 points, I can say the average change of whatever happened between those 2 points is 25/8. So that problem really served, or that problem so far, we're going to do one more thing with it, but so far this problem served to do a lot of reviewing, right? We reviewed working with fractions. I know we all sort of seize up just a little bit in our hearts when we see fractions, but if you just take your time and be careful and don't try to shortcut it. Notice I didn't. I almost shortcut it up here, and I decided, no, I'm just going to do it the longhand way, talking and thinking how to say it to you and writing at the same time. Too many opportunities to make a mistake, so I just went ahead and wrote it out and took more steps. Nothing wrong with doing that. In the end, I got to my value, and now what I want to do is I want to write the equation for that line that goes through those 2 points. So I want an equation for the secant line that intersects the parabola at point 1 and point 2. That's easy enough. We have to use our formula. It's a formula. Y minus the y you know equals m times x minus the x you know. So this is a super important formula for writing the equation of a line. And you want to definitely have it committed to memory. So let's go ahead and figure out the equation of this line that we're working with here. Well, we know what the slope is. It's 25/8. So we can just plug that in. And then we're going to use y minus, we need to plug a y value in there, and then x minus, we're going to plug an x value in here. And which one should we use? So none of them are really pretty, and I'm going to go to the reduced forms, but I think this might be a better one, mostly because since I'm going to be subtracting a y value, this will make it positive, and 1/2 is just a smaller, I think that's just going to be a prettier calculation with these 2 fractions. You make your own choice. It doesn't really matter. Y minus the y I know is 11/4, and then 25/8 times x minus the x I know, which is 1/2. All right, so y plus 11/4, not pi-4, equals 25/8x, so that's the slope, minus 25/16. And now I want to subtract the 11/4 from both sides, but 11/4 with a 4 in the denominator means multiply both the numerator and the denominator by 4, so I get a 16, and 11 times 4 is 44. So this is going to give me 25/8x minus 25 take away 44 is 69. Hang on, let me double check. 40, 50, 69 divided by 16. So as long as I'm doing so much review, or I've already done so much review in this video, let's finish off with a small review of the types of equations for lines. So right here where I started with y plus 11/4 equals 25/8 times x minus 1/2, I could also have written this equation y minus, using the other point, let's see, which one did I use? Using this point, 13/4 equals the slope 25/8 times x minus 5/2. So I could have started with either using P1 to plug into my point slope form of an equation, or by using P2 to plug into my point slope form of equation. The important thing is recognizing that this is the point slope form of the equation. And that it is not unique. In fact, if I wanted to, I could choose other values plug them in for X and get a Y out. And I could have infinite different versions of the point slope form of the equation. Interestingly enough, while it's not unique, the higher you go in math, the more that one is valued, mostly because going from here to here, you can make a mistake. And I indeed may have made a mistake. It's so easy to make mistakes in calculations like this that often once you get beyond the levels of math where you prove you know how to do it, we stop doing it. So for calculus and beyond, you will use the point slope form of the equation rather than converting to this next form, which is the most common form in early math. If I take the y, so I've canceled the 11/4, so now on this side of the equal sign, all I have left is a y. And then over here, I have 25/8 x minus 69/16. This is the slope-intercept form. And this is the form you're most familiar with because it's the first one we teach. It's the one that makes the most sense to pre-algebra and Algebra 1 students. And so we use the slope-intercept form for graphing. And so you've used this form longer than any other form. And really, except for being, notice, well, and I didn't do the math of it, but had I continued this calculation with this version of the point slope form, I would have ended up in exactly the same place. And so this is a unique form. The point slope form for any line is always exactly the same no matter where you look on the line. So this is the form you're used to working with, certainly can always convert to that. And then there's one more form, and it would be the one I would use if I first found a common denominator. And let me fix this mistake I see, 16. I could take this and use a common denominator, multiplying both 8 and 25 by 2 would give me y equals 50 x over 16 minus 69 over 16. And then if I multiply both sides by 16, I get 16y. So I've multiplied both sides by 16. Then I'm going to subtract the 50x from both sides. Equals negative 69, because once I multiply through by the 16, all that's left on this side is a negative 69. And this is standard form. And they're all good now for us. Early on, this was the only form that we knew how to graph with. But now that you've gone through Algebra 2 and as you move forward in your algebra, you will recognize that each form has its own value. So in standard form, I can set either variable equal to 0 and get my x-intercept and y-intercept. Those 2 points connected will give me the line. So if I wanted to graph from standard form, super easy to do. If I want to graph from slope-intercept form, obviously easy to do. This is the y-intercept. I rise 25 and I run 8. I get a second point, connect those 2 points, and I've graphed my line. And from point slope form of the equation, it's not as easy to see, but it's really the same form that we're used to using for parent translations on parabolas and other parent graphs. This video went a little bit longer than I would have liked, but considering that it was mostly review, just really solidifying some background knowledge that you're going to need throughout the course, I think it was worth the extra time.